start slowly because there may be other people coming in these first few minutes. This is supposed to be a research talk, but it's actually a hybrid, okay? Because I decided not to try and show you one thing, but to try and make some sort of a broad overview, putting in pointers to lots of different things. So stop me whenever you want. I know you're not the person you were expecting to see right now. There was supposed to be another speaker first, but there was a cancellation. Okay, so I'm Francesca Chiaromonte, the second one on your schedule for the day. Just as a warning, I think if things work out, what they wanted to do was to move the afternoon talk to the morning right after the coffee break so that we don't have an afternoon talk after lunch. These are the institutions where I work. Penn State is the university where I worked for now almost 18 years, which is pretty scary. And Sant'Anna is a school of advanced studies, a sort of small special university in Italy where I'm spending a lot of time these days. So this is an outline. And as I said, I'm going to give you pointers, almost no detail. But if you're curious, stop me. And especially we can talk about details afterwards. So what I'll do is I'll start introducing what's a supervised problem in high dimension, which is probably familiar to all of you, and try and give you a sense of two different philosophies, two different strategies that statisticians normally use to tackle high-dimensional data sets. Okay, one is feature selection, the other one is sufficient dimension reduction. I'm going to try and spend a bit more time on a special twist that you can have on these strategies that has to do with accounting for structure. Because nowadays data sets are not just high-dimensional, they tend to have structure inside them that is known and that you can try and leverage also while you try and reduce them, compress them. I will talk about ultra-high dimensional supervised problem, because the truth of the matter is that what was meant for high dimension 20 or 30 years ago is really not what high dimension means today. Okay? High dimension meant hundreds of features. Now we're talking about millions. Okay? And that makes a big difference. And if I'll get to it, I'll talk a little bit about functional data analysis. I know that you've had a talk during the retreat by Marzia, so you've seen already quite a bit of that. So I'll just, if I get there, I'll touch upon it. Okay? Am I all right? Okay, so this is just, this shouldn't confuse anybody or raise existential questions for anybody. Recent advances in all sorts of different experimental techniques, as well as the ability of storing data, has made it so that we've gotten to the point where on a single unit, a single sample, a single individual, a single carrier of information, we can measure many, many things at once. Okay? The number of things is p. That's the dimension of the feature space. It is also the case that in what is now called big data, you also have very large number of units carrying information that get to be surveyed or sampled. Okay? So in contemporary big data, you often have also a very large n. Okay? Not just a very large p, but I'm not going to touch on that. A supervised problem in full generality is some kind of, it's a regression or a classification problem, a generalized regression problem, where you have n units, you have one feature that is special because it's the response, it's the thing that you're trying to predict, to explain. And then you have a certain number of features, the x's here, that you use to build a model to explain or predict y. This is just general symbol for that model, okay? It's going to have a certain function, a certain form g. This form usually is parameterized, beta are the parameters. This epsilon here stands for error, okay? Because in the data that you sample from this postulated underlying mechanism, there will be error that you need to account for when you try to predict y as a function of x. In most of what I'll be saying today, we assume that when we get to see the stochastic mechanism over and over again, we do so independently. Okay? In many circumstances, this is not the case, And there are, of course, variants on all sorts of different statistical techniques to account for dependent observations. Everyone all right? Yeah? Okay. What are the issues when P is large? There is an accuracy issue, both in terms of estimating the parameters and in terms of out-of-sample prediction of the response. When I say out-of-sample, I mean you have this data, you use the data you have to train, as some people say, the model, okay, to choose the G and estimate the beta. When you want to assess the performance of this model, you try not to do it directly on the data you have, but out of sample, right? Because that's the true performance of the model. Sometimes you have to fake that because you don't have test data, okay? So you do things to the data you have to fake that, but the idea is to assess out of sample performance. Another issue that raises, that comes about when P is large, for some of the techniques that are employed, is computational burden. Not all the techniques. Some techniques are pretty parsimonious in computational burden, but some can get very expensive when P is large. And also, importantly, there is an issue of interpretation. Okay? So if you want to have a cartoon in mind, think of a situation like this in which you have lots of columns, okay? Often more columns than rows, okay? But for now, pretend I haven't said that. And you're trying to go down to a much smaller number of features if you can. These would be the X tildes, okay? The tilde is not showing entirely here, but it doesn't matter. The notion is that D is much smaller than P, okay? And there are two main philosophies that people use when tackling this type of problem. This is something that actually has arisen already in past talks. One is feature selection, okay? You want to pick D, much smaller than P, among the original features, all right? Another one is dimension reduction. Neglect the sufficient for a second here. When you do dimension reduction, you don't pick features. You create composites of the original features, okay? The easiest example, and the one that people get lots of mileage out, is to make linear combinations of the original features, okay? Of course, there's nonlinear dimension reduction. There are all sorts of variations that you can imagine, but you know, you're not just picking D, okay? You're picking D composites. The term sufficient here, it actually refers to a field of statistical literature that's called sufficient dimension reduction, which is kind of different from the things that you probably have in mind, like principal components analysis, because it's a supervised dimension reduction. You're not just trying to compress the axis based on something that concerns the axis, you're trying to compress the axis based on the intent of explaining or predicting y. Okay? All right. There are sort of basic notions underlying these two types of philosophies. Okay? Underlying feature selection, there's a notion of sparsity. In the back of your mind, whether you make this a strong assumption or not, there's a notion that perhaps you have 1,500 features, but there's really only 5 or 10 that affect your response, and your problem is finding them. Okay? The parallel notion in the supervised or sufficient dimension reduction, you may think of as one of low complexity. All right? Maybe all the features affect the response, but they do so in a sort of low-dimensional underlying informational core. Okay? Have you ever heard, maybe in principal component analysis, when you study principal component analysis, some people refer to the number of principal components you pick as the level of complexity of the data, right? Sort of the intrinsic dimension of the data. Of course, this low complexity doesn't need to align with the original coordinate system, right? This is a reduction in dimension after you rotate the coordinates in your space, which means that in the end, all original features may load on the combinations, but the complexity of the data is low. Feature selection has a clear interpretation advantage. because you start with features you know, you've put them into the problem, right? And you pick some of those and you use them to build your predictive machinery. Interpretation for sufficient dimension reduction may not be so straightforward because you're rotating your problem before you compress it. So your new predictors are, say, linear combinations of the original ones, and sometimes you're lucky and these combinations are very interpretable. They may not be. Okay? On the other hand, because you allow a rotation before you get rid of some of your space, you can reduce a lot more in dimension reduction approaches than you can in feature selection, at least in principle. Does this make sense to everybody? All right. Either way, what you end up doing is, in output of this, is having the small number of new features, either a selection of the original ones or a selection of composites, that you use to fit a much smaller model, hopefully increasing accuracy a lot, reducing computation time, and increasing your ability to give interesting and meaningful interpretations of what comes out of this. There's been, since the early 90s, when these two things kind of took off, principal components analysis is much older than that. Okay? Principal components analysis, factor analysis, and these type of techniques date back to the 70s even. But in the early 90s, with the lasso on one side and sufficient dimension reduction on the other, there was sort of a takeoff of this type of literature in statistics that kind of paralleled the fact that available data started to increase in dimension. Cartoonishly, I'll show you one representative for feature selection, which you probably all heard about. Anyone who's never heard of the lasso? No, very good. So what's the lasso? The lasso is a way of penalizing the objective function that you're using to fit a model. It is model-based. You have to pick a model, for instance, a simple linear form in the axis. Normally, you would fit that by minimizing this expression. You stick another piece onto this, a penalization. And this penalization depends on the size of the coefficients. Okay? On the size of the coefficients measured in a special way, an L1 norm. And the result of this choice is that you tend to make some of the betas shrink to 0. Okay? I'm calling it soft here because you're not saying I want 5 features, okay? Or I want 7, or I want 3. You're going to fix lambda. Lambda is the weight of the penalty term. Depending on lambda, lasso on its own is going to decide if and which and how many coefficients it can shrink to 0. Okay? The other thing to notice is that here you're doing the selection and performing the estimation of the coefficients at once. If you draw this, so this would be the solution without constraints, this is the solution with constraints, this is the shape of the constraint. Another important thing to notice is that that constraint is convex. So this is actually a problem for which people were able to establish very, very good algorithms, very good computation. Okay? It goes extremely fast. People have done it in all possible condiments. Some, hopefully, several coefficients are shrunk to 0. The sampling variability, what you can think of as a standard error, okay, of the estimates decreases. The estimates are stabilized. But you're introducing a bias, and this is an important thing to know. A bias, let's say if the least squares estimator were unbiased because you hit exactly on the right underlying model, the lasso estimator would have a bias. The other important thing to know is that you have to select lambda. Okay? This is not something that you hit with the default, whatever the default in the software is. Because if you take the wrong lambda, you can get really messed up results. Okay? So in fact, the crux of this whole thing is choosing lambda, the weight that the penalty must have, and hence the degree of sparsity that you're imposing on your solution. Usually people, ideally you would want to do this based on out-of-sample performance, say the out-of-sample mean square error. this out-of-sample mean square error ideally should have a sweet spot, okay? Because it's sort of capturing a trade-off between reducing the variance and increasing the bias of your estimates. Of course, you don't know the theoretical out-of-sample mean square error. Usually people estimate it via cross-validation, okay? And try to pick an optimal lambda based on cross-validation. As a warning, many of you probably know this already, it's not always the case that the cross-validation mean square error has a U shape, right? That you can pick a nice sweet spot on. Most of the time it goes down and stays flat, so you have to try and go for parsimonious solutions. I mean, things may not be as trivial as they seem. These are basic references down here that you may or may not want to follow. This now gets a little bit perhaps less known by everybody. People have pushed here, okay, the boundary of this research. And one way they have pushed it is to try and reduce the bias that you're introducing with this machinery, okay? To reduce the bias, you kind of have to abandon convexity. This is my attempt at drawing that as a cartoon. To abandon convexity, you enter the realm of much more complicated computational problems, okay? Much more complicated optimization problems where computation is much less straightforward and usually takes more time. Part of the reason why I went through all of this stuff that I just said is that I wanted to let you know about what seems to be an important recent development, okay? This is meaningful. It's not just an epsilon change, okay? This is a change of perspective. The real feature selection problem, what I'm calling the hard feature selection problem right now, is not really, here's a penalty for having large coefficients, see if you can shrink them, okay? It's, give me 5, okay? How large are these 5? I don't know. It depends on the effect size of these variables, okay? So that, on small problems, a long time ago, was done with what was called, you know, if you've had a basic regression class, best subset selection, right? Try all the subsets of size 1, of size 2, of size 3, of size 4. Decide which subsets of variables you want to pick. But that is computationally viable really only on small problems, okay? So for a long time, it was, you know, this was not considered essentially because going to this super non-convex thing where your constraints are essentially the axis, right? So I want my solution to be on one of the axes because I want to drop one predictor. How big? I don't care. It was not handled directly. It was not fashionable to try and reason in these terms because it was not computationally viable for reasonably sized problems. But apparently, optimization operations research people that study optimization now have ways to tackle this type of problems through something that's called mixed integer optimization. The problem becomes something like this. You see the way you're measuring the size of the coefficient is actually an indicator function. Are you there or are you not? Okay? And what you have to tune here now, this C, is in fact the number of predictors that you're keeping directly. This is a reference to the Annals of Statistics last year, and this is a piece from their abstract. This is actually a quote from their abstract. They claim that they can actually handle this with n in the thousands and p in the hundreds in minutes, or n in the hundreds and p in the thousands in minutes. In the first case, you have provable optimality. In the second case, you have some kind of near optimality guarantees. They also claim that they do much better than the lasso. Okay? You do realize, I'm saying this because I will get back to this later, that this is not the size of problems we usually deal with in omics, right? This is still sort of a toy experiment for relative to the type of data that we usually handle. But it looks like a considerable improvement. What's the catch, though? This may be computationally viable for this size of problems if you sweep under the rug the problem of tuning C, right? If you wanted to tune C, you have to do this many times over, okay? And so side note, I still don't know the timing because now there's been this talk cancellation, so we finish earlier, so blah, blah, blah. But I wanted to mention this at the risk of having, the kids that work with me hate me for the rest of their lives, that two of them, Anna and Debmalia, this afternoon are going to be rehearsing talks that they're preparing for JSM. This is a statistics conference that happens in a couple of weeks. So we're going to sit in here and rehearse the talks. I'm going to just give you pointers now. If you're interested, come and torture them together with me. So they hate us together. I'm not the only object of the hate. Okay. So here I'm just saying that this new mixing integer optimization-based approach is rather interesting because, again, it addresses the real problem, in a sense, the ideal problem that you would want to address, and also because it's got a very It's got a very straightforward way to introduce structure. In addition to saying, I want only C, say that you have groups of variables. You can very easily add constraints that say, and if I get 3 from this group, I want none from this group, okay? Or if I get only 1 from this group, I want at least 4 from this group, okay? And these type of constraints can actually be rather interesting in omics applications. However, and these are the things that we're trying to figure out with Anna, is it really computationally viable when P is large and taking into account the tuning of C? At least in the exploration that we're doing, it turns out that to make it computationally viable, you actually need to come out with especially light cross-validation schemes that are, designed, that utilize some of the structure in that optimization problem, and also with strategies not to explore the whole range of possible Cs, but to do a smart exploration of it. Otherwise, you can't really run it in a reasonable time even on problems of the type of sizes that they were mentioning, hundreds or thousands. Also, we're trying to understand, if it's true that it does better than the lasso, okay? In terms of specificity and sensitivity in selecting the right features, and also in terms of out-of-sample performance in prediction. Oops, always the wrong. It's also interesting to understand in what kind of settings it does better than the lasso. Give me just a second, I'll get to you. In particular, and I'll mention this because again I'm going to go back to this, do we see that it does better than the lasso in situations where the x's are correlated, have collinearities? Okay? Because it turns out that the lasso, like many other methods, it's not clear how well it does, okay, if you have collinearities. And so if this approach is actually more robust than the lasso in performing feature selection when you have collinearities, that could be a very, very useful characteristic.
So can you add in formulation also the L1 and L2 penalties for free in the last net, which might help also?
I don't know that it has been done, and I'm not an expert in optimization, so I cannot tell you how it would change the problem. But
at least the L2 you can absorb it into the
in the quadratic, yeah. Whoops, sorry. Yes. I don't know. Say why. Why would you want to do that?
It's a richer set of models. So again, your alpha
So
sample.
within the lasso literature, at some point they decided to mix the L1 penalty with an L2 penalty that is traditionally called the ridge regression in statistics. And mixing the two penalties had some advantages, in part perhaps in terms of stabilizing against multicollinearity, because the ridge was an anti-multicollinearity disaster type measure. Here you're selecting the features. Maybe that would, perhaps, yes. Anna, do you know if there's anything in the literature that hints in that direction, mixing this penalty with a...
Already a problem with the one, so now you're trying to turn on.
Right. There's everyone. Did you all hear that? Okay. All right, let me try and accelerate a little bit. Okay, this is a representative for sufficient dimension reduction. Some of you may have heard of this, but it's definitely a lot less famous than LSO. Sliced inverse regression. Anybody? No. Okay. Look at this, because actually the key idea turns out to, in implementation terms, is really, really simple. You form a matrix. This fellow here, this is called the kernel matrix in sufficient dimension reduction terms. And this matrix, in fact, if you look at it, is sort of the variance-covariance matrix of the means of groups of observations that are defined in terms of the response. So it's a little bit the same thing you do when you do linear discriminant analysis. Okay? You have a response. If it's continuous, you slice it. That's why it's called sliced inverse regression. This defines groups of observations in your feature space. You take the mean vectors of these groups of observations. You see how they vary in the feature space. Okay? And then essentially you try and go get the subspace where the group means live. Okay? And you do this by taking an eigen decomposition of this matrix. You form your composite predictors based on the eigenvectors of this matrix. This gives you the right directions. They need to be rescaled by the sample version of the variance-covariance matrix of the axis, and we'll get back to that in a second. And then you fit a model in terms of these composite predictors. Separate step. It doesn't happen all at once. It happens in two separate steps. Why is it called slice? Because if y is continuous, you slice the y. Why is it called inverse regression? Because you're swapping roles here. The real regression that you're interested in is the one of y on the axis, but you're actually looking at how x varies as y varies. Okay? That's why it's called inverse regression. The thing to point out is that you're not using the covariance of x. It's not PCA. Instead, you're using the covariance, population level, of the expected value of x given y. M is the sample version of that. So the leading directions of this covariance matrix actually capture the dependence between x and y. You've turned it around, and you try and see in what kind of subspace, of linear subspace, it lives. The same way we had to select lambda or c before, now we have to select t. The number of eigenvectors you take plays essentially the same role. Okay? There are many strategies that have been explored to this in order to do this. Some are based on statistical testing, how many eigenvalues are significantly non-zero, or sequential testing, like take the first, after the first do you need the second, after the second do you need the third. There are techniques based on resampling. Okay? You essentially repeat this operation on after bootstrapping the data, and you try to see for what dimension you actually get a more stable subspace, okay, with some metric to measure changes in subspaces. There's also BIC type diagnostics that have been developed for this. Here are some basic references, and I can give you more. Here, though, I do want to try and have you understand what's the background, okay, what's behind this, because it's kind of an interesting theoretical structure. Look at this thing here. This is a conditional independence. I'm going to look at subspaces S of my feature space and try and look for some such that if I condition on the projection on the subspace of X, Y and X become independent. Okay? Which means that X contains no more information that is useful about Y besides the one that is in this projection. Okay? If this works, I call that a sufficient dimension reduction subspace. I'll have many, probably. Okay? Of course, I want the smallest. So what you do is you take the intersection of all the subspaces that have this conditional independence property attached to them. Under some conditions that are really mild, this intersection satisfies the conditional independence itself, and that's called the central subspace. Okay? This is this low complexity core that you're looking for.
So again, what is the condition you said if this works, if y is conditionally independent of x?
given PS of X, then S is a good subspace. Of course, if you take the whole, if S is the whole subspace, this works, right? Now you're going to try with a smaller one and a smaller one, but the truth is you are hoping to find a very small one. You want the smallest that allows you to do this unfolding, okay? And it turns out to be a well-defined object. Under my condition, it's unique because you can define it as an intersection. D is its dimension. In this literature, it's called structural dimension. And the reason why it's called sufficient dimension reduction is because this resembles a lot the notion of sufficiency in traditional statistical inference, right? In traditional statistical inference, you say that a statistic is sufficient for a parameter if conditioned upon these statistics, you can throw away the data because the data doesn't tell you anything anymore about the parameter of interest in a certain model, probabilistic model setting. Here, what this is telling you is that if you have this projection of X, so a certain number of linear combinations of X, you can throw the rest away because they're not informative on Y anymore. So the projection is sufficient.
Does that assume some kind of structure between X and Y, for example,
No.
linearity?
No.
If they have some
That's
kind
the
of
power of it, that you assume.
crazy relationship.
And in fact, most of the theoretical results that are developed for this, as well as the results for the methods, don't really use assumptions on Y given X, which are the type of assumptions that you would be talking about. Tell me something about how Y depends on X, and then I can prove you that blah, blah, blah. No, what they tried to do always was, if needed, to put assumptions on X, on the features, not on Y given X, under the notion that the features sometimes you can design by experiment, or you can transform to satisfy certain conditions. Okay, your X's, not the dependence. And that's actually the power of this, that most of the methods that have been developed really do not rely on postulating a certain form. Here's a key example, and again, I'm giving this to you on SERP, but linearity condition. This is an assumption on X. Essentially, you want X to be nice. You want the X's to depend on each other only linearly, not to do strange curves or, you know. If that's true, this holds. The span of the covariance matrix of E of X given Y is indeed inside the space that you're looking for, modulo a rescaling. So this is the theoretical basis to do SIR. And it holds with no assumptions on Y given X, only assumptions on X, which needs to be regular, essentially. If it's elliptical, for instance, it works. Notice that this is inside. You may be missing something. So there is another condition that is usually introduced, which is that you kind of assume away the possibility that you're missing directions. Now, to sort of back this without assumptions on Y given X is a lot harder. But to find directions in the right space, all you need are assumptions on X. And in fact, I don't know if you ever saw this, but I'm going to say it because I think it's a... Remember old, ordinary least squares? Ordinary least squares you actually get, you think you're getting it fitting a model. Y is equal X transpose, beta transpose X plus epsilon. If you fit it when that model is wrong, but the X's are nice, you are actually picking a direction in the right space, regardless of how Y depends on the X's. If you're willing to say, my underlying core is one-dimensional, I don't care, I want one direction. If the X's are nice, or if you can transform them to be nice, the OLS is the direction you want. You take that, you make a composite predictor with the fitted value, and then you make a complicated model on top of it. Okay? This is, I think, a powerful thing, and this was actually in the literature in 1989. Okay. Now, after that, though this is not the work that Malia will be talking about this afternoon, but after that, there's been, of course, since the early 90s, a flurry of literature. People have come up with all sorts of kernel matrices, try to mitigate assumptions, doing all sorts of different things, find more informative ones. People have also done local methods, okay, that are actually more computationally expensive, but exploit the direct regression function instead of the inverse one. The man in particular worked on a matrix that we call covariate information matrix. This is sort of an offspring of a Fisher information notion. Okay, again, you don't have parameters in a model setting, but you have this X, and you think of it, the observed X as sort of the parameter that you want to evaluate the information content of. This can be rewritten in terms of other matrices that can be estimated fairly quickly, and then you can take the spectral decomposition, the eigen decomposition of this matrix to find directions in the central space, and it in fact works. This is work under revision, and okay, it seems to perform rather well compared to the most recent methods in the field. And it is completely assumption-free. It doesn't even require that linearity of the X's, the linearity conditions that I talked about before, because essentially you are accounting for the structure of X. You're taking it out of the game within the method. Okay. I don't know how much time I have, but I keep going. At some point we'll stop. This is another very important development. Okay. Structure. As I said, data are not just high dimensional, they're complicated, or complex if you want to say it in a more, in a nicer fashion. There's structure in it often that you may want to leverage, and this should be done both if you're trying to do feature selection and if you're trying to do sufficient dimension reduction. One obvious type of structure is groups. Here are examples of groups that you may be very familiar with from your work. Units, let's say that these are individuals. They can be of different genders, different ethnic origins. They can have different type of cancers. They can be treated with different protocols. They can be in different hospitals. Moral of the story, you can think of them as coming from different subpopulations. Groups of units. Everyone okay with this? Groups of features. Very common in the data that we handle all the time, right? You may have 1,000 features that come from one type of high throughput platform, and then 10,000 that come from another one, and then you could have social demographic covariates relative to the patients. You could have clinical covariates relative to the patients. All sorts of different X's that you want to put in a prediction mechanism that are very different in nature, right? Let's call these feature domains. Can we use this type of information as we're trying to compress a problem by selecting features or reducing the dimension? And important word, keyword here, keep in mind, and maybe you'll see this better with the cartoons that I have on the next slides, that this is a way to do data integration, essentially. Okay? I'm taking data from the various hospitals and putting it together. I'm taking data, assays from different experimental platforms and putting them together. It's an easy, it's integration easier than many other integrations that people try to do, because it can always pivot on rows or columns of your data set, okay? But it is a form of integration. And integrating the data as you're trying to compress a problem can actually be rather effective and rather useful. Okay, so these are grouped features. I'm chopping the columns of my data set and hence making rectangles. I have domain 1, domain 2, domain 3, domain G. Okay? Should domain shape feature selections? Yeah, one obvious instance is that you may want to say, okay, all the features in one group ought to be in or out. Okay? Has anyone seen that already, since you've all seen Lasso? Group Lasso, exactly. But genuine. Should groups shape reduction? Yes. For instance, I may want only features within one domain to be linearly combined with each other, but not with the other ones. Yeah? Maybe I don't want to combine income or some clinical variates with gene expression levels or epigenomic information or information on the microbiome. Okay, so here's two pieces of literature. This is the group Lasso. This is a fairly recent paper that does group-wise sufficient dimension reduction, in fact group-wise SIR, based on something that is called envelope methodology. Fairly complicated, but we'll actually look into that, or maybe not, I don't know. So why I do this? Here I was trying to give you the backbone of the theory behind putting groups in dimension reduction. Okay, essentially you do a dimension reduction within each of the domains, but then you have a problem when you're trying to stack these spaces with each other. Why? Because there can be interdependencies across the domains. If there weren't any, or if there weren't any conditional on the response, then you could just stack them. Reduce, 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 crack. Okay? But since there may be dependencies, you need to account for them. So you have to reduce, 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 and then do something very smart that repositions the spaces that you have obtained within each domain to account for these dependencies before you stack them with each other. Grouped units, similar situation, actually an easier problem, because, and this actually we did a long time ago, partial series 2002. Because if you sample units independently, you don't run this risk of having interdependencies among the subsamples, essentially, across the subsamples. And so you can actually eigenmerge without much trouble. Recently, oh, I forgot to cancel the little arrow here. Okay, we've put these two things together. Okay, so you have data that can have groups of units and groups of features, and we created a methodology that can actually combine these two ways of smartly pooling this information for one direction per rectangle, at most one direction per rectangle. Okay, and this works very nicely. Again, this is the way it's done. We have an inner level, which is essentially group-wise dimension reduction, and then an outer level, which is essentially partial dimension reduction. Okay, so I have a choice here. I'll try to show you one application of this combined strategy where you account for groups both in the features and in the units. This was a prior study. I'm mentioning it because it generated part of the data that we used. And actually, you may remember Prabhani, who was here for the short course. This was one of the papers that she wrote when she was a student with us. This was a study where we took divergence rates, neutral divergence rates, estimated from primal alignments, 4 different types of change along the human genome. Very big windows. These are not the HMMs that we've heard about in the past days. These are HMMs done on very big windows, okay? Hundreds of kbs, even 1 megabase. And we segmented the genome based on this vector of 4 divergence rates. And it worked out really well. I'm convinced exactly because it was not a high resolution, but a lower resolution operation that allowed us to actually tease out large-scale patterns and make a good selection of the number of states. We didn't have 250 states. We had 6. And we could choose 6 with a BIC, okay? Because we could run this thing in a humane time, essentially. These are the 6 states. There is a very hot state. There are a couple of warm states. There is a cold state. There's a super cold state that is essentially chromosome X. And then there's a state where the microsatellites go white. Okay, and what you see here are the human chromosomes segmented according to this HMM. All right, so what we took from here were these 6 states. Okay, these define regions of the genome that appear to be hot or cold based on 4 different ways that the genome has to change. We had these, which represent a categorical predictor. Okay, they separate units, which in this case are windows, in groups. And then we had 37 features that we measured in windows that are, things that in our research group we call genomic landscape variables. Okay, so in these windows we measured all sorts of different things divided in very natural groups. There are variables that are proxy for replication, some that are proxy for transposition, recombination, chromatin structure, transcription, methylation, slippage, repair. 8 groups. P is 37, G is 8, C is 6, and we wanted to use all this information together to predict, explain the prevalence of non-coding functional elements in various locations of the genome, proxied by a variable that we teased out of the ENCODE. There was also an issue here linked to spatial correlations. I'll skip that. The result we got out of applying this scheme that combines your data rectangles smartly is 2 important linear combinations. 2. Okay? One is essentially dominated by DNA is 1, and it's sort of a chromatin domain composite. And it's relevant in hot states, in cold states, in warm states, in all the states. And another one that is dominated by the number of microsatellites, which it's a slippage domain composite, and it's actually relevant only in 3 states out of 6. Okay? If you do an ANCOVA model with these 2 composite predictors and the hotness labels, you explain 77.3% of the variability and prevalence of functional non-coding elements. We had another application that was actually contrasting regions of the genome where you have lots of SNPs, regions of the genome where you have no SNPs, based on the 1000 Genome Project, and regions of the genome where you have de novo mutations, as recorded by the Francesca, Netherlands Genome Project. It starts the same, but it's not the same. All right. And again, we got some very interesting stuff out of this too. You see how there are, how SNPs and de novo mutations have some common things, some common patterns, but also some mirroring patterns that are kind of interesting. Let me just say, you mind if I keep going for another 3 minutes or something like that? I want to say something on this. I'm not going to talk about the functional data analysis stuff, the leveraging of shapes, but I want to say something about this. So the problems I talk to you about right now are not your problems with millions of SNPs, okay? Or with hundreds of thousands of ChIP-seq peaks, okay? They're problems with hundreds, maybe 1,000, maybe they're transcription problems, okay, with some effort, but the problems that we cope with are much higher dimensional. What happens when P becomes ultra high, when P becomes much larger than N? Okay, this is a way of visualizing it. Is it phone? What is this little music? That, It's your relaxing music that Manya turned it up. Now I can torture you twice. Okay. So this guy here, sigma x, is the variance covariance matrix of the axis population level. The sigma hat is the one computed on the sample. Okay? Let's say that you now go to tens of thousands, hundreds of thousands, millions of variables. There will always be a tendency for the sigma x to become more collinear, right? You're putting in more stuff. Unfortunately, the other things that happens is that the one with the hat becomes a lot more collinear than that, simply because you're not observing enough. Okay? It's singular. If n is larger than p, it's for sure singular, and progressively more singular. The data is thin in feature space, thinner and thinner and thinner. This is a plot, and the numbers are not large. N60 P1000, N60 P5000. Okay? These are absolute values of sample correlations when there's none in, you're simulating these data. There is no correlations among the x's. See what happens to the sample correlations. You see? So we use that sigma x a lot. Oops. This is the OLS vector, just to give you one instance. When you compute an OLS vector, you take the relationship, the linear relationship between y and x, and you remap it with sigma x to the -1. This remapping is critical because when you evaluate how y depends on x, you want to scale it with the way the x's scale and relate to each other. Otherwise, it's meaningless. You do this in almost all the standard statistical manipulation, okay, that you can think of. Implicitly or explicitly, you're rescaling like this. But if you have a very poor evaluation of sigma x, even if you do generalized inverses, even if you come up with weird ways not to do the -1, if you are bad at evaluating sigma x, this remapping is poor. It's so poor that you might almost decide it's best not to do it. Okay? And it's not just that the standard model fitting becomes bad, it's that feature selection and dimension reduction become bad. You want to do them to get out of the curse of dimensionality, but you have so little information that you can't even jumpstart yourself out of the curse of dimensionality. These techniques work poorly when there's multicollinearity. Here you have sort of the mother of all multicollinearities, right? So one strategy that, I'll just put it all on and talk first a second. One strategy that people have started proposing from maybe 2007, 2008 is, okay, forget about remapping to take into account the associations among the x's. Just screen, okay? You've got 1 million variables, throw, most of them out at the outset, stay with 1,000 perhaps, and then do your thing on 1,000 variables, okay? These are called screening algorithms. You may legitimately say that, this is what scientists have done forever, right? Have you ever seen a biologist that doesn't want to do the t-test to see what the differentially expressed genes are before they try to run a classifier right? You just screen things based on marginal associations, essentially. Each x with y, one at a time. You forget about trying to remap for the association of the x's because you have too little information to evaluate it anyway. And then you apply your methods once you have screened out many things. The methods that people are developing to do this type of things actually now have a theory behind it. There are conditions under which, for instance, you can prove this thing that's called short screening property, okay? That you're actually, so this is a technique where you try and minimize false negatives. You don't want to throw out anything that you should keep, but you don't care if you keep some more because you're going to do something else to the data afterwards and eliminate whatever you shouldn't have kept. This is essentially saying you're not throwing out anything useful, okay? And it's actually a theoretical statement, is a form of consistency, okay? A theorem, not a theoretical statement. Note this: as n grows and Pn grows too, because in this ultra-high dimensional data, you've got this other little trick, right? I mean, the more people you sequence, the more SNPs you find, right? So statisticians had to change their asymptotics. What else did I want to say? Okay, this is actually what Malia will be talking about this afternoon because he has developed a method. Again, it's kind of a one-dimensional version of the covariate information number to do this type of screens, okay? Which essentially pivot on an evaluation of this marginal association. The very first screens just used correlation, okay, between y and each x one at a time. It was labeled correlation learning. Okay, I think I'll stop. There were all the functional data analysis things, and these are people in addition to the students who've seen. There should be many more here, but it became ridiculous if I tried to put even more. Thank you. No. Do you want to ask questions? You didn't ask me that many questions, huh? Go.
Yes, so the screening thing, so the screening is still based on your marginal effects, and you can see it in the group and sequence.
Yes.
What are the assumptions?
There are many assumptions. Now, another thing that I didn't say, but I should say, is that some screening procedures are model-based, and then you're making assumptions on the way Y relates to the X's. Some are model-free, though. Okay, and the assumptions, the philosophy underlying the assumption is rather complex. It's a non-trivial one. Come this afternoon if you want. Maybe we can discuss this a bit more. As a word, though, whatever the assumptions may be, these are really situations in which you cannot do something else, right? So you might as well try to do this fairly accurately, because but the sure screening property is kind of, it looks like a miracle, right? You go, it's just so model-based, model-free. Another important distinction is that there are some that are one straight shot and some that are iterative. You do it once, you have some way of taking a residual part, you make another pass at it to see if you left in anything in the soup that was relevant.
So I was wondering, what are the, from a practical point of view, how would you compare like LDA to the slicing?
To SIR?
Yeah.
It's actually very funny. They're extremely similar. I don't think they realized how similar they are when people came up with SIR. You know what changes? You see this rescaling that I've been trying to bug you about, giving you very little background, and I don't know if I made myself understood, but oops. You see this? Sigma x to the minus 1. This is the overall sample variance covariance matrix of the x's.
Maybe we can take this offline.
Sure. Yeah. Please go, and if you want, come here, I'll show you.